Okay, good morning, everybody, and welcome to, I guess, the last Monday lecture of the semester. And Michael Kim will teach us about fairness in algorithms or of algorithms.
Awesome. So yes, today I'm going to tell you a bit about a complexity-theoretic perspective on fairness. And yeah, so this is work that I've been involved in over the past few years, trying to get at this idea of algorithmic fairness or algorithmic unfairness. And really the work is motivated by the observation that these days algorithms are everywhere we look. They're not just solving complicated optimization problems for us. They're not just calculators, but really they're implicated and involved in making consequential decisions about people these days. And so, for instance, they're making medical risk predictions. They're running targeted advertising systems. They're driving our cars. And so I use these examples. I think they're nice in the sense that these examples represent a situation where these days, a computer-driven algorithmic decision maker is replacing a human decision maker, where historically in these contexts, the human decision makers have been highly regulated. So if you're a doctor or you want to drive in this country, you have to get a license. If you want to advertise, advertisements are actually highly regulated. Federal law protects advertisements for, say, housing and jobs to protect against discrimination. And so I think this is a situation where as more and more algorithms start to replace humans as decision makers, we need to be able to reason about how to regulate them and how to understand whether they're fair or unfair. And so really, in order to do that, we have to sort of go to the foundations and understand this issue from the theory of computation perspective. And so that will be sort of my goal for the talk today, to motivate this problem and to introduce it to you. So really my goal is to get across the definitions and sort of the intuition for the problem and what's at stake here. So please ask questions. I'm not going to do too many technical proofs today, mostly going to present definitions and intuition. So stop me with questions as we go, and I'll try to remember to repeat the question for the virtual audience. Good. So to start, I think the best way to start is with a motivating example. And this example is of it's inspired by medical risk prediction. And this is actually a cartoon version of an actual science paper, Obermeyer et al. So this appeared in Science a year or two ago. And so what is going on here? So imagine that you're a hospital and you contract out to develop a predictor for a certain disease. I think they were looking at renal failure, something like this. So I'm going to map some predicted risk score, where up here will be high risk patients. Down here will be low risk patients. And what the hospitals did, this was actually a real predictor that hospitals were using. They set a threshold at which, we'll call this tau. The threshold was such that above this threshold, patients received advanced care. So they were deemed risky enough or unhealthy enough that they were triaged such that they got more serious medical treatment. And so what these researchers did in this paper was they sort of went back through historical data. And in addition to this predicted risk score, they were able to reconstruct sort of a true risk score. And what we would love to see then is that somehow the predicted risk tracked onto the true risk very nicely, right? So you'd love to see some like slope one line. This is the ideal, where the predicted risk would match onto the true risk nicely. And so they looked at these predictions, not just overall, but across different demographic groups. What they found was for, say, the Black patients, these scores were actually well calibrated to this line. this ideal line. And then looking a little bit further, they looked at white patients. And what they found was that systematically, these predictions were upward shifted. And so in effect, what did this do? Even though hospitals across the country were using a fixed threshold for diagnosing whether to give advanced care or not, in effect, the hospitals were using two different thresholds for according to the true risk, where the white threshold was considerably lower than the black threshold. So in other words, if you were a black patient, you had to be considerably more unhealthy, considerably sicker in order to qualify for advanced care than the corresponding white patients. So Shafi's asking if it's empirical evidence, and this is correct. This was, an empirical study published in Science. Avi?
If you did this study 20 years ago before algorithms were used, it would probably be the same.
Yeah, so if you did the study, 20 years ago with primarily white doctors, perhaps it would be exactly the same. Turns out like the reasons for this miscalibration are actually sophisticated. The authors sort of cite the fact that the algorithm developers were training their risk prediction to predict cost of care, not to predict sort of patient outcomes. Turns out that in general, across this country, we just spend a lot less money on black patients than on white patients. So there's bias everywhere. There's all sorts of issues here. But what I want to emphasize with this sort of empirical finding is the fact that somehow some grave unfairness is occurring precisely because we were unable to match the true, sort of the predicted risk to the true risk. These inaccuracies in our risk estimation led to a downstream unfairness. Good. So hopefully this motivates what's at stake in this problem. And so before moving on to technical portion of the talk, I want to get to preliminaries. And yeah.
Are there any other partition, not the white and black, of the society that can you match to say that that's like your
Great.
point?
Great. So this is a great question. So here we're only looking at two groups. We're saying the world is somehow split into black and white patients. This isn't the case. And like undoubtedly there would be other splits which maybe might be matched up to each other or might not be. And
even if you do it like socioeconomic splits.
Yep.
Something of this form would be the same.
They didn't look at that, but conceivably it would, or conceivably it wouldn't. And so this is exactly the type of question that we'll be asking. Is sort of.
Just out of curiosity,
Mm-hmm.
difference in, you said they predicted cost of care.
Yeah.
So there are like two factors. Either there's like discrimination, or it could just be that black people tend not to go get care even though they need to. I'm just wondering which of.
Yeah, I don't know I don't know all the socioeconomic issues that here. But undoubtedly, like the downstream effect is that there's discrimination. And so I think it's a good point to for us to differentiate between the root causes and the effect.
It could be, that if you want a condition on people that actually try to get care.
I think this was based on people who actually tried to get care. Good. So good. So we need to formalize this problem to make progress. So here's how I will formalize it to start. So we're going to assume that there's some domain of individuals, which I'll denote X. Assume for this talk that X is discrete and finite. Think of it as everybody in the world is represented by a 32-bit integer or a 32-bit number. Which represents somehow interesting features about the person. Good. For this talk, I'll focus on binary outcomes. Our hope is to predict whether somebody is going to have renal complications or not have complications. And sometimes we'll think about the probability of complications as well. I will assume that there's a distribution, which I'll denote D or D star, that's joint over individuals and outcome pairs. And so the main objects of study for this talk will be predictors. These are just functions mapping individuals to a probability or to a value in the interval 0, 1 that we'll think of as the probability of a given outcome. Ideally, it would track this probability. And so what would we ideally track? Well, we would ideally track this optimal predictor, which I will denote P star, where P star of X is just equal to the true probability. Oops. Just equal to probability under D star that Y is equal to 1, given your covariates X, given your features X. And good. So the name of the game in this sort of realm, and that I want to focus on today, is on learning. And what do I mean by learning? I simply mean that you're given some samples from the true distribution, and you want to return me a predictor that satisfies some properties. What exactly these properties are, we'll talk about. And we'll talk about sort of the comparison to, say, the PAC model as we go along. So good. That's, this issue of algorithmic unfairness is very broad these days. Everybody seems to sort of have unfairness in their different algorithms. This is what I want to talk about today. Yep.
Let's say in this example, the predictor y equal to 0 or 1 would be over tau or less than tau?
Exactly, something like this, or high risk or low risk. Yep, and then, so maybe that the outcomes would be, did you get renal complications or not? Did you get a disease or not? And then the predictor would be this actual score function that you could then threshold at tau. We can think about Boolean predictors as well that would just automatically, these all typically called classifiers. Good. Any other questions before moving on? Okay, good. So to get back to this example and what was the problem, intuitively the problem that arose, the sort of unfairness arose because these scores weren't matched up to each other, right? Across different populations, the same prediction meant different things. So we can formalize sort of that complaint in a different definition that we call calibration. So calibration is, I guess it doesn't appear so much in the computational learning literature, but it's very common in the statistics and sort of forecasting literature. We say that a predictor is calibrated if the following holds. So for all supported values, for all the values that this predictor supports, the following condition should hold. Probability y equals 1 given okay, so let me say it in words. What am I going to do? I'm going to look at the individuals that this predictor says have probability V. Now I'm going to average amongst those individuals. Amongst those individuals should be the case that their outcome probability is in fact V. Right? So it's sort of, I think it's backwards from a lot of, anyway, if that makes sense, great. The point is that amongst the people who the predictor says 70%, 70% of the outcomes should be 1. And we can also define an approximate version of it. So alpha calibration. For this, I'll write it sort of, write it a different way that will emphasize yes. It would, so if your predictor was Boolean, then it would have to be perfect, essentially, according to calibration. Yes, the alpha version will let you make up to alpha mistakes. So I'm rewriting this probability in terms of an expectation and in terms of this optimal predictor that I defined over here. You should convince yourselves that these things are the same. So what am I doing? I'm just subtracting off v and saying that the difference can be no more than alpha.
So why isn't this just back learning if you allow this to happen with some error over the representation of the predictor?
Good. So we'll talk about sort of why it's not exactly pack learning. It's not obvious. I mean, depends how big you let alpha be.
Also, I assume you would allow general predictor to be a probabilistic algorithm that you can also maximize. You can allow everything you stated with high probability over the random.
That's right. So good. So it could be the case that in general, it's I don't think Pack thinks about this, but in general, sort of running things like logistic regression, say, tend to give calibrated predictions. So Pack often will give you calibration. We'll talk about whether this is a sufficient condition or not. Good. Great. So while I erase the board, are there any other questions on calibration? Because this will really sort of be the main notion that we think about throughout the rest of the talk. No, we'll move further than this, and we'll talk like right now. I'm going to talk about whether I think this is a good notion of fairness or not.
So yeah, just I really like the expression. It makes a difference how many values are in the support. I mean, if it was a Boolean predictor, it's very close to that.
Great, great. So right, so somehow calibration, its strength will depend on how many values you give out and sort of what the confidence of this predictor is. So in fact, I claim that calibration, like it seems at least to be a necessary condition in some cases, but we should not think of it in any way as a sufficient condition. And in particular, I claim this because I claim that every person in the audience knows a very simple algorithm for learning a calibrated predictor. And you use it all the time.
Hold on, you're saying it's almost a necessary condition. I mean, it's very unstable in the sense that if you take one level set of B, split it into two level sets which are almost the same, then you basically ruined everything.
You might ruin everything, yes.
And so I'm missing something because I mean you're looking at exact level sets, not approximate level sets. So saying that this is a necessary, you can clearly split a level set to two things which are almost the same.
Yeah. So for like, I don't want to get into sort of measurability issues and everything. So I think it's a good idea to think of alpha as being, say, a small constant, and your supported values as being also like a large constant. So think of P as a score. If you want to bucket, that's fine too. So I think a good motivating example is to think of this, health risk score as being on a scale from 1 to 10, and alpha being, 5%. Good. Good. So what is this algorithm that I claim you all know that gives you a calibrated predictor? Yeah.
Does he get discrete values or finite set of values? Or is it just an individual?
An individual, which I'm assuming to be discrete, like discrete featurization.
The predictor is discrete?
For the, yeah. Exactly. Yep. And we can make all of these issues like we can complicate all of these issues, but let's not today. So good. So what is this predictor that I claim? The mean predictor is calibrated. So what is this predictor? Let's say for all x in my course. In fact, I could do this for any set. P mu of x equals mu equals expectation of y over d star. Problem solved. We're good, right? So why is this calibrated? So how many supported values do we have? We have a single supported value. So I only have to check this condition for that value. So what is the probability that y equals 1, given that p mu of x equals mu? Well, this conditioning didn't do anything, right? Because this is all of x. So in fact, this has to be equal to probability that y equals 1 just across the distribution is equal to this. So in fact, mu and mu, like the predicted value is in fact equal to the average value. Yeah. Intervals, exactly. Right. So if I wanted to, I could round this to get this approximate notion as well. Good. Right. So the point somehow this notion of calibration is incredibly weak, right? Like it seems like a good idea, but really it doesn't enforce much of anything. And in particular, I might be concerned about not just concerned that predictions are miscalibrated, but that they're calibrated but uninformative. So what do I mean by this? I'm going to draw another cartoon where there's two populations, S and T. And I want you to imagine that S and T, their outcome distributions are identically distributed. Let's even say that in half of them, in both, like 50-50 are ones. Okay? And this will be predicted risk again. So imagine that in S, I actually do a pretty good job of classifying individuals into sort of 0.9s and 0.1s. Maybe I could spread this out the other way. And then in T, what am I going to do? Just going to give out 0.5s to everyone. And I claim that these predictions could be the result of a calibrated learning algorithm. That by merging this group together, by merging all of T together, I give out a fixed prediction that could represent their average in the population. But in a sense, this prediction doesn't give me any information that I didn't already know based only on your membership in T. So this is sort of what this phenomenon where you can group large groups of people together and give them the same value. This is something I've been referring to as algorithmic stereotyping, where really the only information I learn about you from your 0.5 score is that you are a member of this group, right? And so this phenomenon where large groups of individuals can be classified in the same way, this is a very realistic concern, especially for groups that are minorities in the population, simply by virtue of the fact that they're less represented in the training data than in than the majority population. And certainly this phenomenon could be exacerbated by underrepresentation in training data. Okay, good. Avi's, one or two panels ahead. So exactly. So what would we really want here, right? Sort of this The problem somehow is that this notion of calibration is allowing us to group too many groups together and generalize in ways that doesn't discriminate based on their true sort of quality. So the ideal would be some notion of individual calibration. And what might this look like? Well, I might want to say that you're calibrated even when I condition on your covariates. So for instance, probability y equals 1 given p of x equals v and x is equal to little x. But this thing is just equal to, conditioning on the value doesn't matter anymore. Because I'm conditioning on the fact that I know which individual you are. This is just this thing that we've been calling P star. This is the optimal predictor. So in a sense, this is the ideal thing that we would love to get our hands on. But the point is that P star yeah, exactly. But right. So I think you can even ignore this for now. Like it's not super important. The point is that only one value should be supported on, like, the predictor is a function. So only one of these values is supported. So really this is for this individual. Regardless, this holds even if I throw away this condition, like that this is what this is equal to. And my claim is that this is unattainable for statistical reasons. Not even to mention computational, but it's from a small sample, it's statistically impossible. Right? If I make no assumptions about the structure within probability of y given x, then this P star could be anything. And if I haven't seen, your outcomes, then I can make no predictions about it. So that's that means that we have to have a different approach. How does good. So I want to talk about how this pack learning typically handles this problem. Right. So typically we don't, especially in practice, we make no assumptions that on the structure of P star itself, but instead the pack learning model makes assumptions about the class of functions that we want to fit to P star. So the first thing you do is you fix some hypothesis class. H, which in this talk we can think of as just a collection of predictors. And then, okay, so we also need to typically fix a loss. Since we're working with predictors, I'll define this squared loss for today, but I think equally it works for the 0-1 loss. And then the pack guarantee says, return me some h such that with probability 1 minus delta, the expected loss of h is close to the optimal loss within this class. So in h that's right. So because I'm not going to make any assumption about P star, obvious correct that this is the agnostic PAC model. And my goal is not to recover a zero error function. My goal is just to recover a hypothesis H that competes with the best H star in this class, right? And so some sort of assumption like this, working with a fixed hypothesis class in the PAC model is necessary, right? Again, because we've made no assumptions about P star, statistically, it's impossible to get a type of guarantee that doesn't work with some sort of hypothesis class. But the point is that precisely because we are in the agnostic model, this thing that I'll call opt, right? Opt of H need not be zero. It's much greater than zero often. And so in other words, we're necessarily in this situation making errors. And PAC does not require us to reason at all about where those errors are located. In particular, they could be concentrated entirely on a substantial and important minority population, provided that we don't make too many more than the best in this hypothesis class. And so there could be many equivalent hypotheses in this class, make different errors in different places that PAC really doesn't discriminate against, right? And so if we want to reason about where errors are occurring and errors within structured subpopulations, we need something beyond the PAC model. Any questions about that? That one's noisy. I was prepared for the chalk. Okay, good. Good. So this, what we've seen so far is that there's some tension between this group notion of calibration and individual calibration. Where the group notion said protect, let's say O of 1 protected populations. Right, we said there are black people, there are white people, and we should make sure we're calibrated on these groups. Maybe there are men and women, we could protect those too, but nothing more than that. On the other extreme, we had individual calibration, which said protect individuals. In other words, protect all subpopulations. Right? If we're going to give an individual level guarantee, this is equivalent in a sense to saying I need to reason about every single possible subpopulation. And we said that this was an information theoretic guarantee that we had no hope of getting. But we would love it. And so faced with an information theoretic ideal that is sort of unattainable, what should we do? Well, a very natural approach would be to give a computational relaxation. Yeah, I should have let you answer. No, but it should be no surprise that in order to do this, we're going to give some version of computational relaxation. And a different way of saying this is strengthening the guarantees of group notions, going beyond protected groups. And so this motivates our definition that we call multi-calibration. Good. And so what is multi-calibration intuitively? Multi-calibration will guarantee calibration across a set of computationally identifiable groups. So protect identifiable groups, where this notion of identifiability will depend on a parameterized computational bound. And we can basically interpolate between this group notion of very weak notion all the way up to this information theoretic notion by defining different variants of it. So say that again.
You put the burden of proof of bias on anybody who claims there is bias. Show me a subpopulation that is biased.
Precisely. So in other words, yes, as Avi's saying, like we want it to be the case that in order to claim that a predictor is biased, you need to be able to witness a subpopulation on which it is miscalibrated or biased. Exactly. So formally, how will we define this? So definition, multi-calibration. I'm going to use MC throughout the talk. Good. So let C be some class of, we'll say, Boolean functions. And so for concreteness, perhaps think of this as functions that are implementable by depth 3 decision trees. Some expressive but fairly simple class. I said decision trees.
Oh, you made it. Oh, it's possible. Yeah. So you just look at three bits of the input and decide.
Sure, that's right. But I'm going to consider the entire class of such functions. Good. So a predictor P, I'll actually use P tilde to denote such functions. Predictor P tilde is C alpha multi-calibrated if for all, let's say, little c in C, and for all V in the support of P, tilde, the expectation of Y given P tilde X equals V and C of X equals 1 less than alpha. So in other words, I want my predictor to be calibrated even when I restrict my attention to subpopulations defined by this circuit class. Right, so I think there should be, like, if you haven't seen it already, there should be a strong like bijection between C and C and some S that's a subpopulation of X, right? Where I'm saying that these C's really define the characteristic function of class of subpopulations that I want to protect. So I'm not just going to require overall calibration, but I'm going to require that your predictor looks approximately calibrated, even when I restrict my attention to these subpopulations. Mm-hmm. Yep. Yeah, and in fact, yeah, it's a great point, and yeah. Yeah, we should. Yeah, so Avi and Shafi are sort of highlighting the fact that a different way of saying this is as saying, think of it as a game between a learner and a challenger. The learner says, hey, I've learned a fair multi-calibrated predictor. The challenger has to look at the predictor and try to find some C in my class that is not that witnesses the fact that you're not multi-calibrated. If the learner learns something that can't be distinguished in that sense, then they win. This is stronger.
Yeah, that's stronger. He wants to have a,
So that's right. So and in particular, it might be possible to get better algorithms that come with provable guarantees. So we're jumping ahead to the fact that learning multi-calibrated predictors is tightly connected to the problem of agnostic learning.
but it's serious issue here because just limiting C is not enough to test. I mean, the testing of this property is not easy.
The testing of the universal quantity.
No. For given C.
Uh-huh.
For given C, may be difficult to, statistically, so you would sample, right?
Exactly. So actually, so I think.
You just care about values that are high probability in this sense.
Yeah. So good. So it's a great point. So suppose I only cared about this for one set, then I claim that we're back into the calibration realm. And what I could do is just sample, polynomial in alpha, 1 over alpha, and logarithmic in the confidence parameter, and be pretty convinced that this on this population, the notion is satisfied. And really the question is whether I can do this simultaneously for all CNC statistically efficiently and computationally efficiently. So that's the bad one. More questions about the definition. Good.
I'm still trying to figure out like if this capital C is just an arbitrary way of measuring hardness, or
it's measuring how rich is the set of protected samples.
Yeah.
What's the kind of how would you define the protected sample? What's the complexity of the set of protected samples? Cannot protect all samples.
Maybe you should just think of C as a sigma algebra rather in a sense. And you just want to be in the
It's always simplified everything.
No, I mean
the sigma algebra works.
Yeah. So that's not how I think about it. The way that I think about C is as a hypothesis class. And I think this analogy is very strong. And in fact, I can make it technical. But the point is, why do I think about it this way? For very simple hypothesis classes, I can have efficient algorithms for learning and statistically simple, bounded VC dimension. I can learn these from a small number of samples. As I move to more complicated hypothesis classes, my statistical complexity and my computational complexity may grow. But if I am able to guarantee a learner for such a class, then the guarantees are much stronger, right? And so exactly the same phenomena happens here.
I think what I'm trying to figure out is if you have some kind of a control on C, so there is some kind of an aggregation level.
This is what he said. So, for example, in learning theory, you have the VC dimension of the class. That's one control. Yeah. So we know they are easier to learn, and we say it's even easier to learn in the multi-calibrated set. And there are more complex ones where the VC dimension is too high, like all polynomial size circuits.
Yep.
And then, if you could guarantee multi-calibration against it, of course, it would be great.
Yep.
I don't know if you can.
Yep, exactly. Good. So I think that one question you should ask is why do we like multi-calibration in the first place? And so I think there are two different answers that I can give sort of with that are quite nice. So one is that you guarantee let's say it like this. You don't overlook qualified subpopulations. In your class C. And two is this idea of robustness to underrepresentation. So I think I'm going to, I think I'm not going to say too much about one. What do I mean by this? It just means suppose that there's some subpopulation. Suppose there's some S in C such that the expectation of Y, what was that? In C. So suppose that within my class, there is some subpopulation such that the expectation of Y for X in S is close to 1. Okay, good. So I'll say C and C of X equals 1. Good, good. So if this is the case, that the expectation is very large, then in a sense, I have to be calibrated on this population. In fact, that means at very least I have to be have accurate expectation. And so my predictions are forced to move upwards and be close to 1 as well on this on the image of C, right? On that subpopulation defined by this C. So what intuitively what this says at least is that C should help identify sort of structure in Y given X. So that's sort of what you want C to do. You want to take C to be as expressive as you can afford to really highlight structure in the conditional distribution of Y given X's.
Why this is better than just just partition X to some number of X.
You remember what you're given. You are just given samples. Given a bunch of samples. You have, if you knew the index of exactly what
So, and I think the point is that somehow this class, this computational class, can help identify the reasonable partitions for you, right? That and help to identify the so an analogy that or an example that I give is, typically, historically in these fairness definitions, people would say protect Black individuals, protect women. And what we're saying is don't think about it marginally in that way. What you want to do is protect Black women who wear glasses. And so you say, why protect people who wear glasses? That's not a protected group. The point is that this additional attribute and additional sort of computational processing of a person's covariates can help you identify structure within the population in sort of the outcome distribution given the person's covariates.
Can I please try to answer? I think I can. So if you set alpha equal to 0, then exactly what you're asking here is look at the partition induced by the class C, and you just want to look at the predictor, which is in the linear subspace that says for every partition group you are what you call it calibrated. That would be exactly the same alpha is equal 0. If it's not equal 0, then you're intuitively what you're saying is the harder it is to describe the group. If black women who wear glasses and have a bigger left ear than the right ear, the more you need, the less accurate you actually need to be because those are other.
But I'm trying to figure out what's the best partition here. You're saying that there is partition is the best.
Also a notion of recognition.
Yeah.
Yeah, the optimal partition is to individuals. There is
No, optimal up to some point.
Exactly. So this is the complexity of the classes. Yeah. And you're trying to capture what the type of complexity and the efficiency are.
There is more information here than just a partition. That's the point. Less important in this just being calibrated for. This is the way to measure fairness.
Good. So I'm happy to participate offline or afterwards. Good. So the main question that we should ask ourselves at this point is whether we can actually learn such things. Mhm. Mhm.
You could have two complexity types. You could have the complexity of the first of the entity of the challenger.
Yeah.
Right? And you could have the complexity of the class that he says that you failed, right?
Okay.
They don't have to be the same.
They don't have to be the same. And I think after these next two slides, I think the discussion will be much more rich. So let's first ask the question about auditing. We want to learn, but now I'm just going to present maybe a simpler problem. That someone gives you a predictor that they claim is multi-calibrated. And your job is to determine whether there exists some C in your class such that the multi-calibration condition is violated, right? And so staring at this, this expectation, I claim that you can rewrite it with perhaps some loss in exactly the advantage as follows. So in other words, because I'm conditioning on the fact that C of x is 1, I'm going to write it instead as some inner product, some correlation between the errors that you're making, y minus the predicted value, and some C in your class. Right, so even further, I can simplify this. For the purposes of this talk, we can think about certifying an even simpler property. Is this large? So exists some C and C such that this is large. And I claim that this is actually a well-studied problem. This is exactly the weak agnostic learning problem. Where what is the weak agnostic learning problem? So it's the problem of correlation detection. Specifically, I'll say that weak agnostic learning with respect to a class C and a correlation parameter rho of some data and some label function is the following. So in this case, our label function is y minus p. Exactly. So if it's okay, I can write it out, but it's exactly this problem. It's if there exists something greater than rho, then you have to return some h, possibly in some other class. I don't care. It's just some function such that the correlation between h and y minus p is, let's say, at least rho by 10. So it's saying that if there's some non-trivial correlation, find me something else with maybe not optimal, but good correlation. Right, and so this is a well-studied problem. It's a computationally hard problem in general because it's equivalent to strong learning by boosting. But in fact, that what we observe and what I think should be clear is that by exactly sort of an analogous reduction, we can go from this auditing problem, from this weak agnostic learning problem, to a learner for multi-calibration. So I can write the algorithm out on the board, but I think the main takeaway is by using standard sort of boosting intuition, you can go from leveraging this weak agnostic learner to a multi-calibrated learner.
So for every class you have a weak learner, you have a
Exactly. So Avi said the theorem is that if C is weak agnostic learnable, then C alpha multi-calibration, multi-calibrated learner. And in fact, we show the reverse implication as well, that a C alpha multi-calibration algorithm implies an agnostic learner. So C alpha calibration implies agnostic learning. It's without the weak, That's right. That's right. And I'm sweeping a lot of details under the rug. In particular, you have to be pretty careful. The way that we're defining conditional expectations versus this sort of absolute error, there's some loss there as well. But up to these constants and polynomial factors, like these reductions go through. So how should you interpret this result? Right. So the truth is that there aren't that many classes that are agnostic learnable. My subpopulations.
I missed what the theorem says. Like it seems to me that S should appear.
Oh, I'm sorry. This is rho. This is rho, and this.
Hold on. So okay.
So I just called it rho for correlation.
But where's the class? Among which you're learning that the other. I see. Thinking. Okay. I see. You're using the same.
No, he's allowing you. It's not. There's no correlation. There's consider correlation. It's allowing you to find a weakness.
Right, exactly. And it is important that you be able to evaluate it, that you be able to present me a circuit that computes this subpopulation, because I'm then going to use this circuit and incorporate it into my predictor that I'm building up. And I claim that after not too many iterations, this thing will converge. It need not be. That's exactly the point. It could be. Like this would be proper agnostic learning, but really I don't care as long as it's efficiently computable. Good. So, right. So, which C can we get this for? Mm-hmm. Mm-hmm. Yep, that's right. Yes, so I'm doing this, the label that I'm using is sort of this residual. It's y minus your current prediction on that individual x. So for all, for x1, I'm labeling it by y1 minus p of x1. And then x2 gets y2 minus p of x2. Right, and so I'm also lying to you over here because I'm probably going to also have to run it on the reverse label, or unless my class is closed under negation.
So I'm sorry.
No, great.
Use any concept. That's one. You just want to learn this. You're not restricted here to concept class.
Yeah, the restriction C is only on the type of population we want.
Right. So.
But like the conclusion does have a concept class in it. Or I'm sure I'm just
it's a concept class on it, but it's not the concept class of the final predictor. It's just a concept class on which we are fighting in this agnostic.
I know.
It just defines the optimum.
But it also has a multi-calibrated learner is not with a specified concept class for the presenter.
That's right. Probably, yes. So the point, like this is a good point. Sort of as we were saying with the agnostic pack learning, we said that if we fixed our hypothesis class up front and said we're going to return a function from this class, then there were inherent limitations to what we could do, right? And there were trade-offs. We're not subscribing to that paradigm. We're saying, these are the collection of populations that I want to protect. Return me any function that satisfies this notion. I don't care how you compute it as long as you compute it efficiently. Turns out that there's a way to implement this, provided you have a weak agnostic learner that returns you a circuit that is not much larger than, say, the complexity of representing these functions in C, or really than the complexity. Exactly. So, and there's I don't want to say whenever, like we use a specific boosting algorithm, but I think sort of certainly statistically, whenever boosting works, it should work, and I think it should be a pretty generic conclusion that whenever boosting works, we can make this work. And in particular, the parameters that you get in terms of the complexity scale very much like boosting.
Okay, so I could still ask, suppose I want something that's close to the minimum of some given concept class, also multi-calibrated, but this is like
you could
another question.
You could.
Got it.
Yes.
Okay, I thought this is what you
Right. So I do not have an objective function.
Okay, I see it.
That's right. That's right. And actually, there are recent results that say that that basically, if you learn a multi-calibrated predictor, you cannot do worse. Like that, you always do better than the best linear combination.
Sure. I guess I just want to say, I mean, just a point to make is that, like in the examples you gave us, a priori there was a concept class that also included, I don't know, some things in your blood tests, blah, 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 not groups that I would a priori care about in the context of fairness.
Mm-hmm.
And then, you know, you also want to add those obviously to see
Yes,
for, you know, when you're using this.
that's right.
But we could also say, you know, I have the concept class, what we call H before.
Yep.
And my fairness is with respect to some completely different thing,
Mm-hmm.
right?
Mhm.
I don't know,
Mm-hmm.
population, stuff like that. And then, you know, a viable question would be, I want to find something which is both close to the minimizer in S and also does not violate multi-calibration with respect to a different concept.
That's right. And if you restrict yourself to proper learning within this class, H, then you will always introduce trade-offs, right?
Sure.
You know, constrained optimization can only do worse than unconstrained. But if you want to use a concept, a hypothesis class H, and be multi-calibrated, there's a way to basically power these classes together such that you can guarantee that I don't do worse than the best hypothesis in H, and I achieve multi-calibration.
Or you could take the level sets you get by H and just
That's right. That's you're reconstructing this argument for why this can work. Yes, exactly. Good. So I want to say one more thing about sort of a different view on all of this. I'll quickly say that this agnostic learning problem is hard for most classes. There are some like restricted models in which you can agnostic learn with provable guarantees, like over the uniform distribution with query access. But there's two comments I would make. The first is if we relax this multi-calibration definition to not be about Boolean functions, but to be about real valued functions, then now this agnostic learning problem is just a regression problem. And there are sort of regression problems that come with provable guarantees. So for a slightly weaker notion of multi-calibration, you can get algorithms for certain classes of functions that give you provable guarantees. The other is that the agnostic learning problem supposedly is the hardest problem in the world, but all of practical machine learning is agnostic learning. And it seems to be working very well in practice. So in fact, we can use very effective heuristics. And basically, the argument shows that we can reduce the problem of multi-calibration learning to just machine learning. So if that's your cup of tea, that also works. Good, but I'll take 5 more minutes, yeah, to give you a different view on these things. So a pseudo-random view on, let's say, learning. And I think it also falls into maybe an imitation game view on learning. So intuitively, this collection C and the tests that we threw in terms of multi-calibration, they define ways in which this P tilde has to look like P star, has to look like the outcome distribution. So I want you to consider, we'll try to formalize this intuition. So consider 2 distributions, 2 different worlds. One is just nature's distribution. Okay, then a different distribution. I'll have x and y tilde drawn from some d of p tilde, where X is still marginal on individuals according to nature. And Y, rather than sampling the true label, I'm going to sample Y tilde according to the Bernoulli distribution based on the prediction given by P tilde. We're looking at Boolean outcome distributions. Yes, exactly. And so a very natural goal would be to say, I want to learn a P tilde that induces a distribution over individuals and outcomes such that D star and dP tilde are indistinguishable. And I'll formalize it through a notion that we call outcome indistinguishability. And so a predictor P tilde is, I'll say, squiggly A epsilon outcome indistinguishable if for all, I'm thinking of this A as a collection of distinguisher algorithms. So for all algorithms in this class, the probability that AX Y star, and I'll give you access to the predicted value, is equal to 1, equal in these two distributions. That I'm not sure. Yeah. Very, very possible. Like it would be. It's a very natural definition. So it's a good definition. It's a good question. I think it's true depending on exactly the model of distinguisher. So I think what's maybe different, maybe not, we should discuss, but that we're giving access also to the predicted value. So I allow you, the distinguishers, to look at the predicted value of P tilde in both distributions. And so when we the theorem that we have is actually that outcome indistinguishability is equivalent to multi-calibration. It's equivalent. So I mean this in a computational sense. That is to say that if you give me a class of distinguishing algorithms, then I can turn this into a collection, a hypothesis class, C or CA, such that CA multi-calibration implies A OI, and vice versa. If you give me a computational class, a C, then I can turn it into a class of distinguishing algorithms. It's even simpler than that, right? So I guess C of A, yeah, might be something like this. A of C is very simple, right? That on the board in right. So for instance, right, let's say suppose you have some C in your class C, then you could define A of C, let's say V of X, Y, P tilde X is going to be C of X not equal to 1 or P tilde X not equal to V. Return 0, else return Y. Right, so if it's the first time you've seen something like that, I don't think you'll see it. But if it's not, then I think we can convince ourselves that this gives us something like multi-calibration. So I think the last point that I want to make is why introduce this indistinguishability notion. The point is that now that we have an interpretation of it as indistinguishability, we can apply our favorite tools from computational indistinguishability to learning problems. So for instance, hybrid arguments. I think, in the paper, we do a lot of work to emphasize this point, but I think, Avi says that randomness is in the eye of the beholder, but maybe this also extends to individual probabilities. So rather than randomness, like this idea of P star. And the idea of the idea of individual risk, what it even means, really is in the eye of the beholder and is in the eye of like how much you want to scrutinize these probabilities. And the final thing that I'll say is we can also introduce stronger distinguishers. So if we allow our distinguishers not just passive access to P tilde, but we instead allow them to have oracle access to P tilde, turns out we can prove that a variant of OI that has oracle access is provably stronger than multi-calibration. So not quite. We had some discussions about this, actually. So I'm not allowing you to query sort of outcomes. I'm allowing you to query the predicted value. Yes. OK, good. Good. Right. So I'm allowing you to inspect the predictor by making queries. Turns out that under sort of fine-grained average case hardness assumptions, like provably you cannot achieve this notion in the same efficiency that you can achieve multi-calibration, which sort of suggests a very practical implication that when auditors are auditing these predictors in practice, we should allow them to have oracle access. We should allow them to query the predictors, not just passively look at historical predictions. Good. I think I'm over time. There's lots of connections. There's lots of interesting questions that are still open. And thanks for the attention and questions along the way.
Thank you very much.